Alright, let's dive straight into how we can make large language models think smarter, not just harder. We're talking about fractional reasoning. So, we know that getting LLMs to do better reasoning often involves giving them more compute time at inference, right? Think generating multiple answers and picking the best one, or having the model check its own work. This is called test time compute. It's pretty effective. But here's the rub. Most methods are like a one-size-fits-all approach. You give them a prompt, say, think step by step, and boom, they all get the same level of deep thought. The problem is, some questions are easy peasy, maybe just need a quick answer, while others are brain teasers demanding serious analysis. If you always push the model to overthink simple stuff, it wastes time and might even mess up the answer. Conversely, if you don't push it enough for hard problems, it'll just guess wrong. We need a way to tell the model, hey, this one's tricky, think really hard, or, nah, this is easy, just give me the answer. That's the core challenge. Enter fractional reasoning, or FR. The name itself gives us a clue. It's about controlling the amount of reasoning fractionally. Think of it like adjusting the volume knob on your thinking. Instead of just saying think or don't think, FR lets you dial in the exact intensity needed. How does it pull this off? It's clever. It figures out what part of the model's internal state gets changed when you use a prompt like think step by step. It captures this change in a vector, a mathematical arrow pointing in the direction of deeper thinking. Then, instead of just applying the prompt blindly, FR takes this vector and scales it using a factor we call alpha. A small alpha means gentle nudging towards reasoning. A large alpha means a strong push. This allows the model to adapt its thinking process dynamically based on the input. It works great for two main scenarios, either boosting the quality of many different answers, like in best of n, or making sure the model thoroughly checks its own work, like in self-reflection. Okay, let's peek under the hood a bit. Why does this steering work? Well, LLMs, especially the big ones, are built using something called transformer architecture. Think of it as a complex network where information flows through layers of attention mechanisms. When you add a prompt like think step by step before the actual question, it's like adding a new instruction signal. Our key insight is that this prompt doesn't just change the final output, it actually shifts the internal representations the model uses to process the question. Mathematically, if you look at the output after adding the prompt, it's essentially a mix of the original output without the prompt and the output influenced by the prompt itself. There's a weighting factor, W, which depends on how much the model pays attention to the prompt versus the original query. The crucial point here is that this shift, this W, is determined by the model's internal workings. It's fixed once the model is trained. We can't easily tweak it on the fly. So, if the model's internal shift is fixed, how do we control it? That's where the fractional reasoning framework comes in. The core idea is beautifully simple. We take that fixed shift, represented by a vector h steer, and we scale it. We add a scaled version of this vector to the model's original internal states h, ORI. The formula looks like this: h hat equals rescale h, ORI plus alpha times h, steer. Here, alpha is our magic dial. It's a number we choose. If alpha is 0, we add nothing, no steering. If alpha is positive, we push the model towards deeper reasoning. If it's negative, we might pull it back from overthinking. The rescale part is important too. It just makes sure the overall magnitude of the internal state stays roughly the same, preventing instability. This gives us a direct, interpretable way to control the influence of the prompt. Now, how do we actually get this magical steering vector, h, steer? We don't just guess. We learn it. The idea is based on contrast. We take the same question and pair it with two different prompts, one that encourages the kind of thinking we want, let's call it the positive prompt, and one that discourages it, the negative prompt. For example, for chain of thought, the positive might be solve this with detailed steps, and the negative could be just give the answer. We feed these pairs into the model and capture the internal representations, the latent states, at each layer. The steering vector h, steer, is then calculated to be the direction that best separates the representations from the positive examples from those of the negative examples. Essentially, it finds the principal axis along which the model's internal state changes most significantly due to the prompt. It's like finding the dominant direction of the effect. Once we have our steering vector h, steer, applying it is straightforward. For each token in the input sequence, we take its original internal state ht and add a scaled version of our steering vector, scaled by our chosen alpha. So, the new state becomes h t hat equals h t plus alpha times h, steer. Again, the rescale step is crucial. It normalizes the resulting state so its magnitude matches the original state h, t. This prevents the internal dynamics from getting thrown off balance. Think of it as carefully adjusting the direction without changing the overall energy level. Interestingly, this operation can also be seen as a linear interpolation. If we define beta equals alpha divided by 1 plus alpha, then h t hat equals 1 minus beta times h, t plus beta times h, prompt, where h, prompt, is the state influenced by the prompt. When alpha equals 0, beta equals 0, we're back to the original state. When alpha equals 1, beta equals 0.5, we're halfway between the original and the fully prompted state. This provides a clear, continuous control mechanism. Okay, theory is nice, but does it work? Let's look at the experiments. They tested fractional reasoning on 3 popular benchmarks, GSM-8K, Math 500, and GPQA. These cover math problems and science reasoning. They used 2 strong open-source models, Qwen 2.5 7B Instruct and LLAMA 3.1 8B Instruct. For comparison, they looked at standard methods like majority vote, where you generate many answers and pick the most common one, and best of n, where you generate n answers and use a judge to pick the best. The setup was fair. They compared their method with FR applied to the prompts against the standard methods. For FR, they generated answers using different alpha values, essentially sampling different levels of reasoning intensity. The final answer was selected using the same method as the baseline, either voting or picking the best. This isolates the effect of FR itself. And the results? Pretty compelling. Across all the benchmarks and models tested, fractional reasoning consistently boosted performance. Look at Figure 1 here. The blue bars represent the standard methods like best of n or majority vote. The purple bars show those same methods but enhanced with fractional reasoning. You can see a clear improvement, especially for the best of n plus FR setup. Why does this happen? Because by varying the alpha, FR introduces diversity in the reasoning process. Some answers might come from a slightly more thoughtful model, others from a less intense one. This broader exploration of the solution space makes it more likely that one of the generated answers will be correct, making the selection process like best of n or majority vote more efficient. It's like giving the model a wider net to catch the right answer. Now, FR isn't just for chain of thought. They also applied it to reflection prompting, where the model critiques its own initial answer. This is another area where uniformity is a problem. Sometimes an initial answer is wrong and you need strong reflection to fix it. Other times the answer is already correct and excessive reflection can just complicate things or even introduce errors. FR shines here too. By controlling the reflection strength with alpha, the model can tailor its self-critique. Table 2 shows the results. Compared to standard reflection prompting, FR leads to better accuracy. It helps the model avoid over-reflecting on correct answers while still providing enough scrutiny to correct mistakes effectively. It's about finding the Goldilocks zone for reflection. The researchers didn't stop there. They explored even finer control. What if we could adjust the reasoning intensity not just for the whole question, but sentence by sentence as the model generates its answer? Imagine the model starts with a low alpha, thinking quickly. But then, as it generates a sentence, a feedback signal, maybe a score from a process reward model, flags a potential inconsistency. At that point, the system could automatically increase the alpha for the next few sentences, pushing the model to think more deeply about that specific part. Figure 3 gives a great example. An initial reflection missed an error because it was too weak. But using this sentence-level dynamic control, the model detected the issue later and adjusted its alpha, successfully correcting the flawed reasoning step. This suggests FR has the potential for truly adaptive, on-the-fly control. Let's dig a bit deeper into how FR actually changes the model's behavior. First, quantitatively, as shown in Figure 4, increasing the alpha value leads to longer answers. This makes sense, more reasoning means more writing. Qualitatively, looking at Figure 2, the differences are stark. With a low alpha, the model is pretty lazy, giving short, shallow answers for Co-T prompts and failing to engage in meaningful reflection. Crank up the alpha to medium, and suddenly you get coherent, multi-step reasoning in Co-T and accurate, insightful critiques during reflection. Push it too high though, and you start seeing signs of overthinking, getting bogged down in unnecessary details, or even over-reflection where the model second guesses itself too much. It confirms that alpha provides a smooth, interpretable slider for controlling the depth of reasoning. Does this work only on general models? Or does it help even models already trained specifically for reasoning? Table 3 answers that. They tested FR on a model called DeepSeek Roan Distill Quen 7b, which is known for its strong reasoning capabilities. And guess what? FR still improved performance. This shows the framework is quite general. Another important aspect is scalability. How does performance change as we increase the computational budget, i.e., generate more samples? Figure 5 plots accuracy against the number of generations. FR shows a consistent improvement as more generations are generated. Interestingly, the standard best of n method, which relies on a judge to pick the best, doesn't scale as well as FR. FR seems to be more effective at shifting the distribution towards correct answers, making it more sample efficient. It's a win across the board. So, wrapping it all up, fractional reasoning offers a powerful, flexible way to control how much an LLM reasons. It's training-free, meaning you don't need to retrain the model and it works with different models. By manipulating the latent steering vectors with a simple alpha, we can dial in the exact level of reasoning needed for each task. The experiments show it boosts performance across various reasoning strategies and scales well with computation. It's a promising step towards making LLMs smarter and more efficient reasoners. Of course, there's still work to do, like automatically figuring out the best alpha for each input, but the foundation is solid. That covers the main points of the paper.